Hello dear students, today we are going to start with the next topic of this chapter, that is third colligative property, depression in freezing point. Now this property is also somewhat similar to the one that we had discussed previously. We had discussed already the two properties, that is elevation in the boiling point as well as the relative lowering of the vapor pressure. Now this property is also somewhere or the other related to the root cause for this property is also the same that we had studied in our previous two colligative properties. So first of all, by the name, what is it? It is suggesting depression in freezing point. It means that it is a difference between the freezing point of the pure solvent and the freezing point of the solution with a non-volatile solute. Now what does this mean? This means that whenever we have a pure solvent, whatever be its freezing point, now whenever you add a non-volatile solute to that pure solvent, always the freezing point of the solution will decrease. This difference between the original freezing point of the pure solvent and the new decreased freezing point of the of the solution is depression in freezing point, denoted by delta TF. Delta stands for the difference between the two. Now what is the cause behind this, that when we are adding non-volatile solute, why is the freezing point decreasing? What is the main cause? So as we have seen that what was the main cause for the elevation in the boiling point, similar is the cause for the depression in the freezing point, that is the lowering of the vapor pressure. Now what does this mean? It means that whenever you add non-volatile solute, the vapor pressure will get lower, and because of that we have the depression in freezing point. Now let us understand how. So when non-volatile solute is added to the pure solvent at its freezing point, the vapor pressure of liquid solvent will decrease because now the non-volatile solute is there. So the vapor pressure will decrease, and hence the equilibrium of the solid solvent and the liquid solvent will be disturbed. Now you should know that whenever we are freezing something, so there is an equilibrium between its solid state and its liquid state. So, and whenever we are the boiling something, then there is an equilibrium between its liquid state and its gaseous state. So here the solid solvent and the liquid solvent have a equilibrium, but this is disturbed when we add the non-volatile solute. Now this was the equilibrium which was earlier present, but now it is disturbed due to addition of non-volatile solute. Now hence, to restore the equilibrium, we have to decrease the temperature till the vapor pressure of solid solvent and the vapor pressure of liquid solvent again becomes equal. Now if we have to restore equilibrium, so according to the theories applied, there is only one possible way to restore the equilibrium, that is if you decrease the vapor pressure. Sorry, if you decrease the temperature, then only this equilibrium can be applied. So this only happens whenever we try to add non-volatile solute. Now again, to attain equilibrium, what will the solution do? It will tend to decrease its freezing point, and again the equilibrium between the solid solvent and the liquid solvent will attain its phase, and we can say that again there will be the equilibrium. But what has happened? The freezing point has decreased. Now you can see from this graph, this is the relationship between the vapor pressure and the temperature. You can see that the vapor pressure and the temperature for solid solvent, liquid solvent, and for the solution. So earlier we can see that at the lesser temperature we had certain vapor pressure for solid solvent, and for more temperature, means suppose for water it is 0 degree Celsius, so lesser than 0 degree we have this solid solvent vapor pressure, and more than 0 we have this liquid solvent vapor pressure. So we have equilibrium at this point. But now because of solution there will be a certain uncertainty that we are getting here, and this uncertainty which has caused is this lowering in the vapor pressure, and this difference between the 2 points will be because this was earlier here, we have seen that this was a freezing point where this equilibrium was maintained, but in the solution this point has shifted here. So the difference between this and this point will be the delta TF, that is a depression in freezing point. So we have seen from the graph that delta TF is directly proportional to the decrease in vapor pressure, and also we know that delta P is directly proportional to XB. We have seen this previously. So by relating these two, what can we write? The new equation, that is delta TF is also directly proportional to XB. Means greater the amount of non-volatile solute, greater will be the depression in freezing point. Removing this proportionality sign, I get Kf. Kf is what? Kf is known as the cryoscopic constant. Now, what is the meaning of cryoscopic constant? As we have studied already in the elevation and boiling point about the ebuloscopic constant. The similar here is the cryoscopic constant. There is no much difference here. If you need to define what is cryoscopic constant, so it is when we put this molality equal to 1. Now how this molality comes, let us see. See, delta TF equal to KF into what it was? It was XB. XB was the mole fraction of solute B. Now XB can be written as NB upon Na plus NB, but since we have a dilute solution, so we can write that the concentration of Na is much greater than the concentration of Nb, so the denominator term of Nb we have neglected. Now I have got this equation. Putting the values for Nb and Na, that is WbMb and WaMa in kg. So I have not added 1000. If it was in gram, that time I can add here 1000 also. So I will get here delta TF equal to KF into M. M is the molality. Now after that we will write this KF as the cryoscopic constant, and if we put this molality as 1, means for 1 molar solution, this cryoscopic constant will be equal to the depression in the freezing point. This is how we define the KF also, just like we did KB. You can learn this value, or else when we solve the numericals we'll get this value, that is Kf for different solutions. Whatever solution in the numerical asked, they will be giving the value. Sometimes if for water they are not giving, so you can learn this is for 1.86 K per m, that is Kelvin per molal solution. Now there are some of the applications for this depression in freezing point, that how is this colligative property useful. Now students, see, first of all application is that it is used to clean the ice on the road in winters by adding CaCl to solution, which decreases the freezing point by minus 50 degrees Celsius. Now see, you know what is the freezing point of water, that is 0 degrees Celsius. Means in atmosphere, whenever there is a temperature of 0, the water will freeze and ice will form. Now what do we do is we add a non-volatile solute, that is calcium chloride. And already I told you that whenever we add non-volatile solute, the result will be that your freezing point will reduce. So it is reducing by 50 degrees Celsius. Means after adding this non-volatile solute, now when the atmospheric temperature will be minus 50 degrees Celsius, that time the water will freeze. Why? Because now it has the non-volatile solute, and because of the concept that we discussed previously, now its freezing point is decreased. And we know in atmosphere we can never ever have this lower temperature, so the water will remain in the liquid state only. Understood this? Let us see the second one. It is used to select a suitable antifreeze, that is alcohols, to be added in the water in the radioactive in the cold regions. Now what do we have is, we use in our car engines, we use a type of antifreeze solution. Now what is the use of that antifreeze solution? So that the liquid which we are using in the engines does not get freeze. Now how do we make it such a way that the liquid is not freezing? It is very simple, by adding again the non-volatile solute. So this is only that it can prepare antifreeze solution of the alcohols. Third, we can calculate the molar mass again, as we are doing with the all colligative properties. Here also we can calculate the molar mass. We should know, by putting this we have to find out the molar mass of solute, that is Mb. If we have to find out, we'll send it here and we'll bring this Kf, we'll bring this delta Tf down. So Mb will be equal to Kf into Wb into 1000 upon delta Tf into Wa. This Wa, when it is in grams, it will be 1000. So this is the applications of the depression and freezing point. The next colligative property is the osmotic pressure. This is the fourth and the last colligative property. This is also very important colligative property. Now you should know that this osmotic pressure is represented by pi. Now first of all, before discussing osmotic pressure, we should understand what is the meaning of osmosis. So osmosis is the spontaneous flow. Spontaneous means which happens automatically. It is a spontaneous flow of solvent towards the solution side through semi-permeable membrane is called osmosis. So whenever the solvent flows towards the solution side, through a semi-permeable membrane. Now, what is the meaning of this semi-permeable membrane? There are many semi-permeable membranes which exist. Semi-permeable membranes are those membranes which allow the specific substances to pass through. Now, there are some of the artificial semi-permeable membrane. For example, you have a cellophane membrane, that is an artificial membrane. You also have the natural semi-permeable membranes. You have that liver membrane is there, and some other membranes are there which can be used here also, so that to make it as a semi permeable membrane. So these are of two types, artificial as well as natural. Now when the solvent molecules flow from the solvent region towards the solution region, this process is called osmosis. Condition is that it flows through the semi permeable membrane. Now why is the solvent molecules flowing? As in the solution, we have non-volatile solute which lowers the vapor pressure, but on the solvent side, now see, solvent is pure, but when we added non-volatile solute to the solvent, that time it converted into the solution. And we know that the vapor pressure of solution is less because non-volatile solute is added. But on the solvent side, we have high pressure. Why? Because no solute is present. As a result, the solvent flows from higher pressure to the lower pressure. Now, this is the basic theory that you should know, that always the molecules will flow from the side which has the greater osmotic pressure to the side with the lower osmotic pressure. So, suppose if I draw it over here, this is my semi-permeable membrane in between. Here I have solvent and here I have solution. Always remember that the osmotic pressure is greater here and here the osmotic pressure is less. So always the molecules will flow this way. Okay. So here also we are doing the same, that the molecules are flowing from the solvent side to the solution side. Now what is the meaning of, okay, this is the osmosis and this is passive, this is not active. Active where we require energy, we require ATP and those all things. This is a passive process because it is happening due to the pressure gradient developed. Now there is one term which is osmotic pressure. What is it? The external pressure that must be applied on the solution side. Means suppose you have here piston also. Okay, suppose this is one piston and here also one piston is there. Now whatever pressure that you have to apply here, so that these molecules do not come here, means you are applying certain pressure here. Because of that, the molecules of solvent stop coming to this side. This extra pressure whatever you have applied, or this external pressure, means which you applied on the solution side, why? To prevent the solvent molecules to come to the solution side, is known as the osmotic pressure. On the basis of this, we have total three types of solutions: hypotonic, hypertonic and isotonic solutions. Now what is the meaning of hypotonic solutions? Hypotonic solutions are those which have a lesser osmotic pressure. Okay, suppose I have a cell here and my surrounding has is the hypotonic solution, so its osmotic pressure is comparatively less, and its osmotic pressure is comparatively high. So now what will happen? Okay, wait, if it should be greater and it should be lesser. So in that case, from the greater osmotic pressure, the things will flow inside. Okay. Second is hypertonic, when we have the greater osmotic pressure. Where we should have the greater osmotic pressure? Greater osmotic pressure should be present inside the cell. That time only outer environment will be hypertonic. Means hypertonic itself is a lesser osmotic pressure, but we are talking with respect to cell. So cell should have a higher osmotic pressure than the surroundings, so that from greater pressure it will move towards the low pressure areas. As a result, what will happen? The cell will shrink. Here what will happen? The cell will swell and burst. Isotonic solutions are those which have the equal osmotic pressure. Now there is one application here. We have when we give glucose or some kind of dose, we always use 0.9% NaCl solution. Why it's so? It is because to maintain the isotonic conditions. Otherwise, if you are giving directly the NaCl solution to the patient's body who is dehydrated, who had got dehydrated due to some reasons, then that direct NaCl solution will act as a hypertonic solution. As a result, what will happen? The cells will shrink, and or second thing can also happen, that if that is dilute, more dilute, that the cells will swell and burst. Which cells? RBCs inside your blood. So this can be a damage to the cells, and this can be lethal also. So to prevent that, we use 0.9% NaCl solution, which is acting as isotonic solution to our body cells. So this is the basic concept of the types of solutions. Now some factual data says that osmotic pressure is directly proportional to temperature, as well as osmotic pressure is directly proportional to the concentration. These two things are there, means greater the concentration, greater will be the osmotic potential or osmotic pressure. So in the solvent side, we had the greater solvent molecules, so the solvent concentration was more, hence its osmotic pressure is also more. So as a result, the solvent molecules flew from the higher osmotic pressure to the lower osmotic pressure. So these two things are to be known. So we can write that osmotic pressure is directly proportional to C into T. This, let us suppose C. So osmotic pressure directly proportional to Ct. Remove this proportionality sign, you get R. R is the ideal gas constant which we already used. And here it is, but this is not that R. Here it is the proportionality constant, and this proportionality constant has a unit which is bar or ATM, which we use over here. So we can write here it is a bar or it is a ATM. And the C, which is concentration, is actually molarity, which can be represented by number of moles of solute upon the volume of solution in the liter. So that is N by V. This is the formula of osmotic pressure that you have to learn by heart. Now osmotic pressure is a pressure, that's why the unit will be Pascal. Now there are some of the applications of this osmotic pressure which you have to learn. First of all is again the same, that is to calculate the molar mass of solute. So to calculate the molar mass of solute, we already know pi equal to CRT or MRT. This is molarity. So substituting this, we can write as N by V or WB upon MB multiply by this V. If it is in ml, then here we'll put 1000. So we have written this thing, and RT is there only. Now this also you can learn, and by here you send this MB over there and bring this pi here. So what we'll get? We'll get MB equal to WB into 1000 in the case of milliliters into RT upon pi into V, which was in ml. So this is there. This is the first application of osmotic pressure. The second application of osmotic pressure is to determine the molecular mass of polymers. Now there are some of the molecular mass of polymers which we can determine. Now polymers and biomolecules have a very less molecular mass. It is an order of daltons, which are very less compared to the normal solutions which we use in chemistry. So only this osmotic pressure is the one which can measure these in the terms of significant, means in the terms of relevant digits. Like suppose if you calculate the molecular mass of polymers or other things by using the other three colligative properties, you get a very small value which is nearly negligible. But in the case of osmotic pressure, you get a good amount of value, you get a bigger value as compared to the other three colligative properties. That's why this is used to determine the molecular mass of polymers. And there is another reason also, that it is measurable at room temperature. Osmotic pressure can be measured at room temperature, while the other three colligative properties require very specific things that are to be applied. After that only we can actually have the proper amount of values. In the next class we are going to study about the Van 't Hoff factor, what is it and what is its role in the colligative properties, and basically it is for the ionic compounds which get associated or dissociated, as well as we are going to understand the concept of abnormal molar mass.